G'day, Richard Walding here from Brisbane, Australia. I'm just going to talk to you today about some experiments senior students can do in electrochemical cells. Let me just show you the slide that I'm using for this. This is a presentation I did at the University of Queensland in conjunction with the Science Teachers Association of Queensland. A lot of chemistry teachers there, and I was going to talk about problems that occur with electrochemical experiments. Let me just go back and tell you how this all came about. Now, before I became a chemistry teacher or chemistry and physics teacher, I was an industrial chemist, and at a cannery called Golden Circle, here's one of the products we used to make. It was Golden Circle fruit salad. You can see it's in a tin can. Well, that's just a tin coated steel, so it's tin plate. The problem was the tin was breaking down inside these cans and you're getting a very tinny taste. Now the scientists couldn't work out why this was, because the tin should protect the steel and there should be no reaction with the fruit juice contents in the steel, or very little reaction. It was under cathodic control, so the tin was acting as a cathode protecting it. But something was going on and they couldn't work out what was wrong. It took about 3 years to work out what was going on in this fruit salad. And it was only this fruit salad that they were making that caused the problem. Now they had universities in the US, Africa, South Africa and England working on this as well as the scientists or the chemists at Golden Circle. They finally tracked it down to what was happening. Now what it was in the end, it was quite simple. It was this stuff here. Now, you might have seen these. These are pawpaws or papaya, and they're grown in Queensland, grown everywhere in the world. But papaya or pawpaw was used in the Golden Circle fruit salad. And what was happening is the nitrate in the pawpaw was reacting with the tin, and you're getting breakdown of tin. So you're getting about 200 parts per million tin in the solution, and that was no good. So the problem was the farmers were using a lot of ammonium nitrate on these pawpaws. Okay, so they're using ammonium nitrate fertilizer, causing high nitrate levels in the pawpaw. And so it took them a long while to work out that it was the pawpaw that was doing it. Now they had a choice of two things: either coat the inside of the can with a lacquer or use low nitrate pawpaw. And one of my jobs there as a chemist was to measure the nitrate in pawpaw, and the farmers would get paid a smaller amount if there was high nitrate in the pawpaw. Okay, so let's move on. Now I'll go to this slide here again. Okay, so that's the title of the slide. Now I just mention that again just so you can see the name of it and the spelling and so on. And there's the pawpaw or papaya. Okay, what I want to do today is to talk about some experiments that senior students can do in galvanic cells. And then this is part A. And then I'll do part B, which will be about electrolytic cells. Okay, in the syllabus, the Queensland syllabus, it talks about a mandatory practical, so all students have to do this, and it just says construct a galvanic cell using two metal and metal ion half cells. Typically, this is what they do. Okay, now this is taken out of the Oxford textbook, but it's similar all over the place. It's not a very good photo. I think it's been photoshopped, but hasn't been done very well. Anyway, you can see you've got two solutions. In this case, you can see it's a zinc sulfate and a copper sulfate with the old spelling of sulfate. And there's a salt bridge you might be able to see. It's hooked up to a voltmeter. Now, the voltmeter is reading 1.89, and this is for a Daniel cell, which is zinc and copper, which should be a maximum of about 1.1. There's also, looks like AC there, so it's measuring the AC voltage, which is not right. It can't. So I think this is just an image they put together somehow. It's a bit distracting. Anyway, let's have a look at this mandatory experiment and what we can do, or what students can do to carry it out. Now this is not the one for the student experiment where they modify the mandatory one. This is just a mandatory one that most students in the world will do, this sort of experiment. So you're measuring the voltage of the various combinations of half cells. In this case, the dependent variable is the cell voltage. And let's have a look at the independent variable. We could use different combinations of half cells. So we can use a zinc and zinc sulfate one. We could also alternatively use a copper and copper half cell as the other half cell. So they make up the combination of half cells. But if you look at the prac, you'll try magnesium and iron and aluminium and silver and all sorts of combinations. This is the one I want to concentrate on, which is the Daniell cell, because it's fairly straightforward, and we can talk about that as a model for the different types. Okay, so in the normal mandatory experiment, you use 1 molar solutions of zinc ions, zinc sulfate or zinc nitrate, 1 molar of copper ions, and then typically you use a salt bridge of potassium nitrate or sodium nitrate or ammonium nitrate, anything like that, something that doesn't react with the half cells. Salt bridge concentration, usually saturated, or at least a few molar potassium nitrate. The area of the salt bridge is not controlled, but you'd use the same time. It might be strips of paper so many centimetres wide and so many centimetres long. You'd have the electrode area, which was the submerged area, would be kept fairly constant, but it doesn't really matter for this sort of experiment. And the distance between the electrodes would be kept fairly constant. And the temperature would be just room temperature. Now that's the mandatory pack. Now I talk to teachers all over Queensland and I've asked them for their student results. The results vary between about 0.6 of a volt up to about 1.8 volts for the same prac all over Queensland. And obviously there's problems there. Now that's why I raised that at the beginning, to talk about the problems chemists had trying to identify the source of the corrosion in cans of fruit salad at Golden Circle. It's not easy, and for students to work out why their pracs aren't working as expected, it's also not easy, and it's hard for the teacher to advise them on why it's not working. But we can have a look at some possibilities in this video, in this presentation. Now in Queensland, students have to modify that experiment to come up with their own student experiment. Now it's called student experiment internal assessment item number 2, IA2. Now they can either refine the original experiment. Now typically by refining they might use more replicates of each test, or use a better quality meter or something like that. Extension, you might do it over a greater range, so you might have a greater range of half cells, or use different concentrations. A redirection, this is probably the most common one for students to do. They look at how the concentration of the different half cells affects the relationship, or the temperature, or something like that. Now, some of these variables make no difference to the cell voltage, and so students end up spending a week trying to get different results, trying to get some decent results, and they go nowhere because they don't work. So the advice is from this presentation is for teachers to try and guide the students into experiments that will allow them to demonstrate their knowledge of electrochemistry. Okay, so we're going to use the Daniell cell for the IA2 student experiment. Now that's the cell reaction. You can see it's a zinc and copper, so zinc half cell and copper half cell. The zinc is oxidized to the Zn2 plus, so that's at the anode, and the copper 2 plus is reduced to copper, and that's at the cathode. Okay, so let's have a look now. That's what we were starting with, the cell voltage as a dependent variable. What can we change and what can we keep constant to make sense of all of this? Okay, let's use potassium nitrate again. Let's keep it saturated. Let's keep the salt bridge area constant. We're going to use the half cell will be the zinc half cell for the anode, and the copper will be the copper half cell for the cathode rather. We'll keep the temperature at a certain temperature, a constant temperature. We'll keep the electrodes separated the same way, the electrode area is the same, and the cathode, let's keep the cathode half cell species is copper, that's from the Daniell cell, and the anode half cell species will be the zinc. So they're all the possible variables. The question is, what can we vary? We need to vary something and have a look at how the cell voltage varies in relation to it. Okay, so I'm suggesting we could use the independent variable of the concentration of the zinc. Now alternatively, and that way you'd keep the copper constant. Alternatively, well, there's the range I'm suggesting. Now I've suggested that range because it provides a reasonable current at a voltage that the school lab power supplies can provide. So somewhere in that range, and we could keep the cathode half cell concentration of copper constant. So there's the dependent variable, the voltage. The independent variable will be the concentration of the zinc. Okay, and you could also try changing the temperature in a separate experiment. So maybe, you know, the typical experiments go from just below room temperature up to medium temperature, not too hot. You start to have all sorts of risk assessment problems. Okay, now what the fundamental part of the way you can explain the relationship is using the Nernst equation. Now before we go any further, let me just say clearly now, the Nernst equation is not a part of the Queensland syllabus, the syllabus in senior chemistry, so students don't have to be able to use that in an exam. They don't have to talk about it in their student experiment write-ups or anything like that. But it gives them and gives teachers an idea of what to expect when they're doing these experiments. So let's go through some of the points. The R is in the equation is just the gas constant. The T is the temperature in Kelvin. This F is a conversion factor to convert moles of electrons to coulombs of electrons. It's just a simple conversion factor. N is basically the charge on the copper or zinc. It's the valency, or actually it's the number of electrons required to react with one atom of the zinc or one atom of the copper. Okay, and that's why I said we'll use the Daniell cell because they're both 2+. Now, in chemistry it's usual to convert this LNQ, and Q is I should have said this, Q is this value down here. It's called the activity, this is the Q value, which is the relationship between the reactants and products. So it's the concentration of the Zn divided by the concentration of the copper. Okay, so that value is just a fairly straightforward, simple value, and you take the natural log. Ln is the natural log of that. Now, I was about to say, in chemistry, students more typically prefer to work with log to the base of 10, and the simple conversion is just a 2.303 in the equation to convert lnq to log to base 10q, but everything else stays the same. So let me just show you a simple calculation, because students might want to do this if they're going to use the Nernst equation. And about half the student reports I see, the students refer to the Nernst equation. They don't need to, like I said, they don't need to, but they certainly seem to like doing it. But they can still get full marks without even referring to it. Okay, so a simple sample calculation would be this. Let's imagine we've got 1 molar zinc sulfate and 0.01 molar copper sulfate, 25 degrees C. So I plug all the numbers in, the 2.303 RT on NF, and so on. So here are the numbers. the gas constant R times the 298, which is the Kelvin temperature, 25 degrees C in Kelvin, divided by 2 times 96485, or 96500, a lot of students use, log 10. The zinc is on the top, so that's this 1 molar. So the Zn2 plus is 1, the copper 2 plus is 0.01, and you end up with 1.04. Okay, now you're probably thinking the E0 cell is 1.1. Well, that's true if you're using the right temperature here, the E0 cell temperature, the standard temperature, and concentrations of 1 molar. Now actually, I know some of you might be saying, well, it's not really the concentrations, it's the activity. But at these sorts of dilutions, activity and concentrations are basically the same. Or you could at least think the factor you multiply this by, the activity coefficient, is the same for top and bottom, so it cancels out. Okay, if you don't want to use the Nernst equation, if you don't want to actually do the calculations, there are plenty of these Nernst equation calculators on the internet. You just plug all the numbers in and it'll come up with the value for it. Now I've done one here. I've put in 1 molar, the concentration of the zinc is 1, the concentration of the copper is 0.01, and we know the Z value, or the valency, is 2. There's the temperature. There's the standard reduction potential that you can get from tables, 1.10, and so on. And you can just click solve the equation, and here it is. Here it's 1.04. So it's just a simple one. There's the link if you want to use it. Let's move on. Okay, so in the first experiment, we could try changing the concentration of either zinc or copper. Now, I said to change zinc, but alternatively, you could change copper. So you can. It doesn't really matter. It's a bit trickier to get high concentrations of copper. Copper sulfate is not as soluble as zinc, or as soluble as the nitrate. So just be careful with the maximum concentration you're going to use for either of these, that it doesn't exceed the solubility. You can look that up in tables. Now you want a big difference. The bigger the difference between these two values, the bigger the log value, and therefore the bigger the impact on this part of the equation, and it'll have a bigger effect on each cell, because you're going to measure the voltages using a voltmeter, and I'll show you in a minute, you're talking about small changes. Now I'm just going to suggest, let's try zinc 2 plus is 2 molar, so that's a fairly big number, and the copper, you could vary it from 0.001 molar up to say 0.5. Now you could go up to 1 molar if you wanted to, or you could, some of my students have done it as 0.0001 molar. The problem I think you do get is with these dilutions, they're very easy to contaminate. I'll mention that later. Now if you go to my webpage, seniorchem.com, there's a whole lot of hints about the concentrations and the solubilities and what's the best thing to do. Okay, now if you do this experiment, here's the zinc concentrations along the bottom. Now this is based on the Nernst equation. You can see you get a lovely curve. Now that's a theoretical curve, but in practice the students don't get anything, or they do get something like it, and I'll show you my results in a minute. Now instead of doing zinc along the bottom, I should mention this as well, students and teachers often say, how many variations of the dependent variable should we use? Should it be 5 by 3? Now that means, should there be 5 data points or 5 variations of the independent variable times 3, so 3 replicates or a triplicate for each one. 5 by 3 is okay really if you've got a linear relationship, and often you don't know whether it's going to be linear or not, but if it's going to be linear, 5 by 3 seems to work. The syllabus doesn't say anything. It gives some hints in some of the reports that 5 by 3 is probably okay, But for non-linear, I would suggest something like 7/3, particularly down here where you're getting quick change. Up here it's not so important, but I'd be concentrating my my variations down here in the 0 to 0.2 region to make sure that's a nice smooth curve. Okay, just be careful with serial dilutions. 1 drop of this 1 molar, because students probably will do serial dilution, so they'll make up 100 mils of 1 molar, then take 50 mils of it and then dilute it maybe half and half, and they'll end up with 0.5 molar and dilute it half and half again. Trouble is, when you're getting down to these 0.0001 molar, 1 drop of this stuff from here can double the concentration down here. And it only takes 1 drop just to, 1 drop left over in a measuring cylinder or something like that, or on a stirring rod or whatever, can really throw out the experiment. Okay, now if you do it the other way around with the copper as a variable, you get basically the reverse graph. Okay, now I don't need to go into that anymore, it's just the reverse of the other one. Have a look at my results. That's the next thing you can do is get Excel to work out the equation for the curve. So I've put a log, asked Excel to give me a logarithmic trend line, and then I've asked for the equation for the trend line, and it comes up with this, and it says it's lnx, so it's the log of the concentration, which we know from the Nernst equation is what you'd expect. Okay, the 1.1, that's basically this top line here, and that is the E0 cell. Okay, 1 molar of copper and 1 molar of zinc should give you E0 at the right temperature, the standard temperature. Okay, question is, what are students supposed to say about that sort of curve? In their report, they probably, all they need to say is that it's a curved relationship between the voltage and the concentration of one of the ions. It's non-linear. Okay, and you could talk about the relationship in terms of the trend line if you like, but some students don't do this. They'll just keep it simple. So if they talk about the fact that it's non-linear, a non-linear relationship, that it curves quickly for the low concentrations of copper and then levels off for the higher concentrations, that could be enough. Okay, now I won't suggest students do this. If they're physics students, they might try and linearise, so they plot log of the copper on the bottom, because I'll just go back a slide. It's suggesting that the trend line is linear if you plot log of x, which is the copper. Okay, so let's plot log of copper on the bottom, and you get a beautiful linear trend line, and you can then work out the slope and all sorts of things from that. I haven't done that, but you could get the equation for the trend line. In physics, students would do that to verify that it is a logarithmic relationship between voltage and the concentration. But the general chemistry students wouldn't need to do that. They wouldn't be expected to anyway. But in case they do, I'm just putting that here so that you are aware of what they might come up with. Here's my experiment. Now I did the 6, it looks like, 1, 2, 3, 4, 5. I did 6 variations of the copper, and I did 3 replicates for each one, and I asked Excel to put a logarithmic trend line, and I got that, and here's my equation. Okay, it's suggesting the E0 value of the cell is 1.05, so there's a little bit of error in my cell, that's somewhere in there. The R squared is very high, so that means the line is consistent with the data points, so it's a good fit for the equation. My data is a good fit for this equation. It's saying it's basically a 99% fit. Let's move on, and I just plotted the log, and you get that equation there. Now you saw the 0.015 before 45, and you saw the 1.05 for for the E naught. So that's consistent with the earlier prac. I'm not suggesting you do it, but if someone does it, you're aware of what they're trying to do and you can guide them. Students who are watching this might like to do it. You just have to be careful of the number of words you use and so on, because there's always word limits that cause problems. Okay, now another thing you could do is compare the experimental values. There's mine, the blue line, with the theoretical according to the Nernst equation, and you can make a comment about how the shape is similar. It's just a loss of voltage. There's a voltage drop of about 0.05, so it's about 0.05 volt error in my results. Okay, there's the two equations for the trend lines, and you can see 1.09, which is basically the standard cell voltage, E naught cell, and here's my experimental one. Now you could also plot the log values of those, and let's have a look. Okay, so as part of the error analysis, you're looking at the validity of the experiment. So in other words, how accurate are your data compared to the accepted values. Now, so I'll go through this. It's up to you whether you, when you're students, whether you talk about this, but I'm just showing you what it looks like. So for the gradient, the accepted value I showed you before was 0.0125. The experimental value, and then the accepted value for the intercept is 1.09, which is the E naught cell at that temperature. The experimental value I showed you on the graphs was 0.0145 and 1.05. Now the error is just the difference between the accepted and the experimental. So there it is there, and it's 0.0020. That's volts per degree Kelvin, or volts per Kelvin. And as a percent, it's that value, the 0.0020 divided by the accepted value. So this formula here, it's from my physics book, but it's used throughout the world. It's not in the syllabus, but it basically says the absolute error, and the absolute just means forget about pluses and minuses. It's just the difference between the accepted value of x and the observed value, or your experimental. And over here, it's just expressing it as a percent. So there's a 16% error in the gradient. Now students could comment on that. That's fairly high error, so the graph is not responding well to the concentration changes. It's not agreeing with the Nernst equation. It's out by 16%. And for the intercept, which is the E naught cell, there's a difference of 0.0396 volts, and which is only 3.6%. Now that's good. I always say to my students, anything under 5% for a senior chemistry experiment is pretty reasonable. Okay, so look, I've just plotted the linearized versions of all of that, and you can see the gradient is a little bit different. Okay, not much, but a little bit different, and the E naught values you can see off over here are out by about 0.05. Okay, I don't want to continue any more with that. We want to move on. For students who are away, they might like to use my data here. So there's some sample data they could use if they wanted to. Now they could use that for practice. Teacher could give them that for practice to plot graphs, or if they're away. Now I think it's important to realise that if a student can't collect their own raw data, they can use someone else's raw data. Now that sounds like it doesn't make sense. It's not raw, it's second-hand, but it's still raw data. It's the data that has been unprocessed. So I'm saying this is still raw data and can be used, as long as they acknowledge in their report that they've got it from this website or from another student or whatever, because they were sick or they were away or they were at some sporting competition, they couldn't get there, representing the school for something. Okay, so the next experiment is the effect of temperature on the cell voltage. Okay, back to the original Nernst equation, or in chemistry terms with the log. Okay, so what we've got to be careful about is the Q value. Now, the Q is just zinc divided by copper, the concentration of zinc divided by the concentration of copper. If the zinc is greater than the copper, you'll have the Q being a number greater than 1. Okay, if it's equal to the copper, that'll be equal, and therefore, then the log of a number greater than 1 is a positive value. And so, as temperature increases, so as T increases, this whole thing gets bigger, so the E cell voltage drops. Okay, so that's the effect of the negative in the equation, so it'll decrease. If they're equal, the Q value is 1, this concentration quotient is 1, the log of 1 is 0, and there won't be any change. So there's no point really in doing an experiment where you have the zinc and the copper the same concentration. Okay, if zinc is less than copper, like I've said here, the log will be negative, and so you'll have a negative of a negative, so it'll be a positive value for the second part of the equation, and therefore the voltage will rise, so you get an increase. So it's up to you and the students what they choose. There doesn't seem much point in not getting a change, because it's not as much of a story to talk about when you're writing a report. Okay, here's my setup. You can see I've got the same cells, the same 2 half cells, and I've got a thermometer probe in there, and at 17.4 degrees I was getting 0.881 volts. At 61 degrees I'm getting 852, so it's dropped as you'd expect. Okay, the voltage drops as the temperature rises. That just confirms it. Okay, so it's a linear relationship, so you'd really only need 5 data points, but I've used 6 in this case, and I've only done it once. I was rushing through this. I didn't do 3 trials. It's really just to show you what it'll look like. But you get a nice straight line. Now, it's not a big voltage difference. Look, 0.8, that's about 0.88 down to about 0.85. So that's only 3 digits in the second decimal place. Now, these meters can read to plus or minus 0.01. Okay, so 0.3 is just outside the limits of reading for the voltmeter, for the voltmeter. So that's why you need to keep the concentrations with a bigger difference as you possibly can. Okay, there's the temperature for. I've done one experiment there, and here's one. These are student results. Now, in this case, this is a student I had a couple of years ago. She used 3.5 molar zinc. Now that's pretty concentrated, and 0.0001 molar copper. Okay, so she was getting a fairly big change. You think she was getting from 1 down to about 0.98 volts. Oh, it's still only 0.02. It's not a big change, but you can pick it up, particularly if you have your voltmeter set on millivolts, which is what she did. You can see get more decimal places. Okay, and I've just put the Nernst equation value in orange on that one as well. Okay. Now I've just added some error bars, so you can play with the error bars and get a trend line through it and all that. I won't persist with this any longer, just to show you what they could look like. Okay, again, if the student's away and you want some raw data for them to work with, here's my set. Now this is genuine data. I've taken this at home, or in the lab I should say, at home, and just a whole lot of data. I haven't processed it at all, so like I said before, if they're away they could use it, or if after a week of collecting data it all fails and they don't get any results for whatever reason, they might use this raw data here. Okay, it's still raw, but you just need to acknowledge it. Okay. The third thing with galvanic cells or electrochemical cells, you can actually do a concentration cell. This works well. Both electrodes are copper, both solutions are copper, they just have different concentrations. Okay, so you start off with low concentration in one and high in the other, and after a period of time they even out. Okay, so one solution produces the copper rod produces copper ions, so there's an oxidation there, and then you've got reduction here, so you decrease the copper concentration there. But in the process there's electrons moving through the external circuit and positive and negative ions moving here to equalise both sides, and you do get a voltage. Okay, I've said 0.02, and when it comes to equilibrium there's none. Okay, here's the equation, the Nernst equation for it, concentration of the dilute divided by the concentrated. That's a neat little experiment. Oh, there it is with the log 10, and then here's my results. Okay, so these aren't theoretical, these are my actual results. You can see most of the points fit the trend line goes nicely through those points, so I was pretty happy with that. That's what students could get. And I've seen a few students do that experiment. They don't get very good results, but I think it's more from contamination really. Anyway, let's move on to electrolytic cells. Now, this is not as common. The students don't do this as often as they do the electrochemical cells, but it's a valuable part of the syllabus. Okay, look, this is the suggested prac in the syllabus. It says use an electrolytic cell to carry out metal plating. That's all it says. That's from the Queensland syllabus. Okay, and the syllabus, I don't really want to read this, but it just talks about the content that they have to get from the when doing this part of the syllabus. This is the subject matter, if you like. Now I've put it here. You can slow down the video and read it, or you can go to the syllabus, and there's predicting the products and so on, E0 values, concentrations and so on, and the essential components of an electrolytic cell. Now all of this is a part of the syllabus subject matter, so any of this could appear on an external exam. So that's why I think it's valuable to do an experiment. Now it's only a suggested experiment, so not all schools do it, and they don't have time. But those who do it, there's a nice little prac in a lot of the textbooks. There's one here out of Oxford. So I've taken this, I've modified it a bit, but it's out of the Oxford textbook. It's just talking about electrolytic cells. So you basically got two copper electrodes. One's the anode, one's the cathode, hooked up to a power supply, just a laboratory power supply, and a solution of copper sulfate. You can see as the reaction is forced to go, one liberates Cu2 plus ions, and the other gains Cu2 plus, which are reduced to form a coating. So this is what it looks like. You get one being worn away as the copper turns to copper ions, and you get a build-up of copper ions on the cathode, a build-up of copper atoms on the cathode as the copper ions are reduced. Okay, so in the student workbook, this is how the Oxford authors have put the diagram for it. You can see it's basically the same idea, except they use a little cup. That's what I tend to use. Look, I'll just go back and show you what I've got here. I just use this little plastic cup. It's very much the same, and I've just got the electrode, over the side, bent over the side, and it's very simple just to clip that on like that. Okay. Now the good thing about these little cups is that you can have your solutions made up with the lid on. Okay, whatever concentration you have, there's 1 molar, and then take the lid off and put the solutions in, or connect the electrodes up. Okay, let's move on. Here's more of a circuit diagram. Now, there's the power supply. I've mentioned the electron current. Now, this might seem a bit odd to chemists. Why would I mention electron current? Why not just call it current? You realise, of course, the physics students learn current as the conventional current, which is the flow of positive charge. So in physics we have to be careful that we're talking about either conventional current or electron current. So just to make sure there's no doubt about it, I've called it electron current. Okay, my copper anode and cathode in the little solution. I've got a voltmeter between the two terminals, okay, and then an ammeter in the circuit. Okay, you can have a look at that diagram later if you're trying to connect it up. Power supply 0 to 12 volts. We usually run at around about 8 volts. That way you get a reasonable current flowing through the circuit. Okay, here's the setup I used. I've just got an ammeter here. Okay, so current I in amps. I used a thermometer, a digital thermometer. You can see this rod in the solution, but you could use a glass thermometer if you like, alcohol in glass one. So that's reading 18.4 degrees C. I've got a stopwatch because I might be timing this. I've labelled the anode and cathode here. There's the metal with the alligator clips on it. I've got a voltmeter over here, okay, and you can see it's reading V in volts, so that's reading 8 volts. It's reading 0.39 of an amp over here because I've got this set on the 10 amp scale, you can see here. So that's reading whole numbers of amps. Okay, so let's move on. Now, to look at the theory behind electrolysis, we need Faraday's first law. And he just proposed that the mass of the elements is directly proportional, or deposited at an electrode, that's the cathode, directly proportional to the charge in Q, in coulombs, which has the symbol C, or in amp, or ampere seconds, okay, which is just, ampere is current, I, seconds is time in seconds. Okay, so basically it's the mass is proportional to Q, the charge, and you could extend that by saying Q equals IT. So the amount of charge in coulombs, now that's basically a physics term which we'll convert, is equal to the current in amps times the time in seconds. Make sure students put that in seconds. Now you can also rearrange this and get rid of M and put in number of moles and get rid of the proportional sign and put in various constants. And I've listed the constants here. N is moles, M is mass in grams, V is the valence, which is 2 plus for these ions, or the number of electrons needed to deposit one atom of, say, the copper. F is the constant between coulombs and moles, so the number of electrons, the relationship between the two units, which chemists are familiar with moles. Physicists tend to use coulombs, which is, it's just another number like moles or dozen or whatever. It's just a number. Okay, and that's the conversion factor. So we end up with replacing IT for the Q, we end up with N equals IT on VF, and instead of N, if you like, we could put in the mass, which we know as N times M from chemistry. So you end up with a formula M equals the molar mass of the copper times the current in amps times the time in seconds divided by the valence, which is 2, divided by Faraday's constant, which is all of that. So that's what we're going to work with when we're looking at possible changes. Now, here's an example just using Faraday's equation. I've given you the current and the time, and calculate the amount of current, amount of copper in moles and then in grams. So you just substitute in 0.2 amps times 15 minutes, which is you need to multiply by 60 to get it to seconds, times VF, and you get 0.00093 moles, and then you can convert that to grams. Now I've shown you a calculation there because students will do that, or students want to know how to do it and not get tangled up. There's a whole lot of different versions of this using Zs and all sorts of things, but this is the simplest way to, I think, to explain it to students. Okay, let's have a look at the suggested experiment. Now, in the suggested one, we just had the dependent variable was the change in mass of the anode and cathode. So you can either measure the decrease at the anode or the increase at the cathode. Now they should be the same value, except one will be a decrease, one's an increase. Now when I do this, I find that they are basically equal. Surprisingly, you think it's unusual to get such good accuracy, if you like, but they're both about the same. Now you could either measure just the cathode if you're trying to keep the time for the experiment down. You've only got a week really to do it. You could just measure one, or you could measure both and average them and look at the uncertainty. But that's starting to complicate it. But I've done that and it works pretty well. Okay, so the suggested one is using copper sulfate as the ions, concentration of 1 molar, 60 mils in one of those little cups. Keep it at room temperature. The electrode are both copper. Electrode area, they say 7 by 3, and that's just a strip of copper, 7 centimetres long by 3. Now that's not the area under the surface of the liquid. That's just what you could start with. Separation distance, well, it's just either sides of those little cups. Voltage, about 8 volts is a good one to start with, but anything over the E0 cell would be good. Oh no, it wouldn't even have to be that. Just need a high voltage to get things, make sure you're getting a reasonable current. The current in the prac, in the book, they don't measure the current, they just set it at 8 volts and let it rip and let it go for 10 minutes. Now you can change all of that by sticking to the same dependent variables, but doing this. Now keeping that the same, keeping that at 1 molar the same as before, keeping that the same, that's the same, that's the same, keeping that the same, that's the same. Now setting the voltage at 8 volts, you're not actually measuring it, but I'm suggesting you could measure it, and the current might be one of the independent variables, because Faraday's law says that mass is proportional to current, and it also says mass is proportional to time. So you've got 2 experiments there. I'll go back, 2 experiments. This is a problem with the voltage and current. Students in the chemistry classes don't often realise that they've got to really watch what's going on here, otherwise their results are back to front. Okay, here's a typical power supply. Now this is an IEC one, these are about $200. The trouble is, as the cell resistance decreases, so if you had a cell and all of a sudden the resistance of it is decreasing, in other words the conductivity is getting it greater for whatever reason, the voltage doesn't stay at 8, it drops and the current varies. It's not designed to put out 8 volts and keep it at 8. These are fairly cheap power supplies, even though they're $200, but they're just robust power supplies. It's up to you to measure the voltage and to maintain it at 8 volts or whatever you want. What I've done is bought a regulated power supply. This one's from JCar, $200, so it's about the same price, but you could get it to be a constant voltage source or a constant current depending on what you need. Now you can notice here I've got it set at CV. You can see the little green light, it says CV, constant voltage of 8 volts. So I'm keeping the voltage constant, so no matter what I do in my experiment, it'll always churn out a difference of 8 volts. At the moment it's 0.145 amps. Okay. Alternatively, you can do the CC. You can see this little light here is CC, constant current. So it's putting out 0.200 amps, and to get that, the voltmeter has to go up to 10.79 volts, or somewhere high to do that. So this is my constant current source now, rather than constant voltage. Okay. So here's some possible modifications. Now there's the equation I had before. What are some of the changes you can make in the independent variables? Well, I mentioned 2. I mentioned current. You can see I. So I will affect the mass. The mass is directly proportional to I if you keep T constant. You could measure the time, or you could use the time as the variable, and the mass will be proportional to the time if you keep the current constant. You could change. Now students like trying this one, the concentration of the copper, but what you'll notice is that there's no mention of the concentration of copper in the Faraday equation, so it has no effect. Okay, so they're going to be a bit disappointed with the results, and in fact they often get results back to front. I'll tell you why later. You could change the area of the electrodes. That's another favourite, but there's no mention of that here. Electrode separation distance, no mention of it, so no effect. And temperature, there's no mention here, so no effect. And I've asked the question here, what's the point of doing experiments 3 to 6 if there's a null result? They'll all be no change. But here's the problem. We will get delta M proportional to I, that's the expectation. We will get that proportional because that's the expectation from the equation. But like I said, M is independent of C. So you should get nothing, you should get nothing, you should get nothing, and you should get nothing. So again, why do it? But I'll tell you why in a minute. Okay, so let's try the effect of current. It should be linear. Look, it's a beautiful linear graph. There's my blue line, the trend line, and there's the theoretical. Okay, I've got the equations for the trend lines here. Okay, so that's worked beautifully. So that's a great one for students to do. I've actually done this. Look, I've got triplicate readings and I've added my error bars. There's a lot to talk about there. It's gone through the origin, which is nice. If it hadn't, there must be probably a systematic error in there for some reason. Okay, the second one, this is just some sample data for students who can't be at school or can't do it or it doesn't work. But again, still raw data, but acknowledge it. So that's there in this video if they want to use it. And that's real data. I took that myself. So it's got enough error in it to make it interesting. The second one is the effect of time. And again, time will be proportional to mass. Mass will be proportional to time. Let's have a look. There's my research question. And there's my result. Beautiful straight line, my dotted line there. A little bit of systematic error here. It's not going through the origin. The trend line, the theoretical value, of course, does, because if time is 0, mass should be 0. Okay, now that's probably because of the uncertainty in the meter. It's the limits of the scale reading uncertainty really for the voltmeter. I think that'd be the main cause, or even for the mass. They're dealing with fairly tiny masses down here. Okay, so that's a nice one. Now here's some raw data I've collected. So this is real data, and students can feel free to use that if they get stuck. And again, my 3 warnings here, or 1 warning, acknowledge the source, and so on. Now I'll go past that. Students, you can stop the video and get that down if you want to. Now, the problem is you're trying to keep if you keep the voltage constant, are you assuming the current will be constant? Well, you think if the resistance is not changing, that's true. But here's the problem. If you increase the copper, this is experiment 3 where I said before there should be no result. The trouble is, if you increase the copper ion concentration, the conductivity of the solution increases because of the greater number of ions. Therefore the current will increase because you're not controlling the current, you're just controlling the voltage and hoping the current will stay constant, but it won't, because the conductivity is increasing, the current will increase, and of course if I increases, the mass will increase. Now students interpret that as you increase the concentration, the mass increases. It doesn't agree with Faraday's equation, but now if they say in their rationale, I'm expecting an increase in conductivity, therefore an increase in current, therefore an increase in mass, they're understanding what's happening. Now the same for the area of the electrodes. Increase the area, you increase the current, therefore the mass increases. Separation distance. As you decrease the distance, the current goes up because there's less distance for the ions to move, and therefore the mass will increase. And lastly, as the temperature increases, the conductivity increases. The ions become more mobile, the higher temperature, therefore the current increases, therefore the mass increases. So, no, you can't assume that if you keep the voltage constant, the current's going to be constant. the current will vary for these. So just be aware of it if students suggest any of these, particularly number 3, which is a favourite. They can run into problems. And here's, I'll just go through a couple of these. This is the concentration one, and keeping current constant. Well, if you do keep current constant, there shouldn't be any change. Okay, if I is constant, there shouldn't be any change when you change the concentration. And this is what I got. Okay, so straight line, you wouldn't that's what you expect. Concentration makes no difference. If you keep the current constant, in this case at 0.2 amps, beautiful straight line. Look, I've got the error bars. You might think I'm rigging this and made it up, but look, it's 0.01. That's the scale reading uncertainty for the balance I was using. I was using a balancer, centigram balance measures to do decimal places. If you can get the balances, that'll read to 3 decimal places. Now they're very expensive. They're probably $2,000 each. These are only a couple of $100, but you could get better results. Okay. If you keep the voltage constant, remember I said the current will change. Okay, so let's keep it constant at, say, 8 volts and see what happens. Okay, we're keeping the voltage constant, so the current can do what it likes. And this is what happens. Okay, so as you increase the concentration, the conductivity increases, so you get an increase in the current, and therefore that's an increase in I, and therefore an increase in M. Okay, you get a nice graph really, and there's a simple relationship between concentration and conductivity. They're basically, they're not exactly proportional, but you could look that up. So that's the logic, which all makes sense. Okay, and I went through that before. Okay, but you also get an increase in temperature. The bigger the current, you get what we call joule heating, and the energy, the electrical energy, gets turned into, or converts into a higher temperature. So you're increasing the temperature, therefore the conductivity also increases because of the increase in temperature. So there's 2 things increasing the conductivity: the concentration and the temperature. So, you're starting to get into a region where not a lot is being controlled. Okay, now this is one student sent me her results and said, I can't work out why I'm getting the exact opposite. And she had uncontrolled voltage and current, and was getting actually a decrease in mass. So I'd put that down to all sorts of problems with the experiment, possibly because the voltage and the current could have dropped. Remember I was saying, depending on the power supply, the current can decrease because it's not putting out a constant current. If you use a good quality power supply, you might be able to control that. Okay, so she was in a bit of a panic about that and just had to write it up with talking about errors and the limitations of the result and so on. This is what she should have got. Okay, so it's a sort of opposite. There's one other problem that can be a problem, one other source of error. It's called feathering. As these copper ions are produced by the electrolyte, by the oxidation of the copper, you get a build-up of concentrated copper ions, and they're more dense, so they sink to the bottom of the beaker, and they swirl over here. So you've got this high concentration at the bottom of the beaker, if there's no stirring, and there tends to be, because of the high concentration, there tends to be a greater source of reaction at the bottom of these 2 electrodes. And actually the little particles of copper can start to stick out, being attracted all the way across, and they form a short circuit. So the current, instead of going through the solution, actually just bypasses it, goes like that, and all of a sudden you're putting the right current in, but you're not getting any increase in mass because it's short-circuiting. So that's called feathering. You could stir the solution to avoid it, but then all of a sudden you knock all this copper off. It causes a bit of a problem. But in industry, it's stirred. Okay, mass and area. So you could change the surface area. Doesn't come into it, but you get a decrease in, or an increase in conductivity, and therefore you get an increase in the mass. Look, I've given up doing the mass. I didn't bother because I knew what would happen. Basically, you just get an increase in current because as the electrode submerged area, which is the area of the electrodes, you just get an increase like that. Okay. Now, some students could look at that and say, there's a linear trend line through there. Well, if they want to do that, that's explaining it nicely. They don't have to Faraday's law is not a part of the syllabus, so they could just say linear trend line, that's the relationship I'm observing, put in my error bars and get an equation, a linear equation. They could still get full marks. Those who understand it might do a look at some sort of inverse relationship here, or power relationship. Okay, it's sort of like a square root relationship. Y is proportional to the square root of the area. It's got that square root sort of look. But you also get an increase in T. And there's the logic. Okay, and what else have we got? Oops. Electrode separation. Of course, as you get it further apart, you get lower conductivity, so lower current, and you get a decrease like that. That makes sense. Students could do it, explain that, but explain it in terms of these points at the bottom. And mass and temperature. How does the mass vary with temperature? And of course, as I said, the conductivity increases with temperature. You can get this out of tables on the internet, conductivity and temperature of copper sulfate, and it looks like that. So you'd get a mass versus temperature looking similar. Okay, and that explains that. Okay, that's the end of my presentation. I've got a lot of hints on my website at seniorchem.com. It goes through all of those experiments but gives dozens of hints for each experiment. For those who want to look at some graph questions based on electrolysis, I've put them on my webpage here. They're just electrolysis graphs where the question is interpreting the graphs, and sort of questions you use on a data test but also in an external exam. So that's the end of that. Thank you.